This is screencast 17.2, the second screencast of chapter 17 on equilibrium. Today we're going to be talking about a very specific type of equilibrium called solubility equilibrium. But in order to discuss that, we need to go back a little bit and talk about what we've been looking at so far. And whether you know it or not, the only instances of equilibrium you've been looking at are called homogeneous equilibrium, where the reactants and products are all in the same state, meaning solid, liquid, or gas. So for example, look at this one here. Hydrogen and fluorine gases combine to form hydrogen fluoride. And note they're all in the same state. They're all in the gaseous state. And remember how to write an equilibrium constant. KEQ, I'm going to write over that. KEQ is always written as products over reactants with coefficients as exponents. Here's another one for the Haber process, also homogeneous. All three are gases, and once again, here's the equilibrium constant. But today we're going to talk about something a little bit different than that, and that's of course called heterogeneous equilibrium. And as you could guess, heterogeneous equilibrium occurs when reactants and products are in multiple phases. And there are some important rules about writing equilibrium constants for this case. First of all, the concentrations of solids or liquids, pure phase materials, are constant. So as an example, let's take a solid, a chunk of iron. If we double the size of the block of volume of iron, we've doubled the volume, and we've also doubled the number of moles, so the moles per liter is the same. It's a constant value. Same with a liquid. If you double the volume of water, you've doubled the number of moles of water, and therefore the concentration is constant. So we're going to have to do something about that. Let me give you an example first before we move on. And in this example, we're going to be dissolving a pile of salt. So the red dots symbolize a pile of regular old table salt. And as you can see, this is an ionic compound. So as it dissolves, the dissolution reaction is shown right here. And as it dissolves, it of course breaks up into sodium ions and chloride ions. Those concentrations are equal to each other because there's as many sodiums as chlorides. But what if I were to increase the size of the pile of salt? Let's make it double the size. Now, this is a saturated solution to start with. We had a pile of salt in the bottom and no more could dissolve, so it was saturated. Even if I double the size of the pile of salt, double the mass, that's not going to change the concentration of sodium and chloride. I cannot dissolve any more salt. That's the definition of equilibrium. So the equilibrium constant for this expression would not depend at all on how much salt is present. So we ignore solids. The same would hold for pure liquids. So in writing equilibrium constants for heterogeneous reactions, we have to ignore the presence of pure solids or pure liquids. So that's written right here. When you write those K expressions, again, look for the pure phases, solids or liquids, and you're going to ignore them, okay? The only thing you care about when writing equilibrium constants are just aqueous phase and gas phase, which can be mixtures, so they're not pure phase materials, okay? So let's do a couple of examples of this. Let's say you're given this reaction, you're asked to write the equilibrium constant for this. So methanol is produced. Now here's methanol. That's what the formula for methanol is. Produced by reacting carbon monoxide gas with hydrogen gas. Now notice there is a pure phase material here. I've already underlined it right there. It's a liquid. So we're going to ignore that in the expression. And when we write the equilibrium constant, it's going to look something like this. Okay? KEQ is equal to products over reactants with coefficients as exponents. Now, the product is a liquid here. We ignore it. It's a constant, so we're just going to write 1 for that. But these are gases, so we are going to write over the concentration of carbon monoxide times the concentration of hydrogen squared, because remember, coefficients as exponents. Let's look at another one. Okay, another example, magnesium oxide reacts with carbon dioxide gas to produce solid magnesium carbonate. Looks like this is balanced already, so this will be an easy one, no coefficients as exponents. But remember, we've got to ignore any pure phase materials. So we've got a solid here, we've got a solid here. So products over reactants, we're just going to have 1 there's the reactant, there's the product, over the only reactant that is to be included. So in this equilibrium, the amount, let's say, of product produced, the amount of magnesium carbonate produced, doesn't depend on how much magnesium oxide is present. It only depends on how much carbon dioxide is present. Okay, so I'm going to move forward a little bit and talk about something a little bit different, and that's what we're leading up to, and that's solubility equilibrium. You guys already know this first part, right? There's a solubility limit. It's called saturation that compounds can dissolve to. It'll dissolve in water until that solution is saturated, right? So let's take salt as an example. When we initially put salt in water, there's no salt dissolved yet, so that reaction goes in one direction only, to the right, forming sodium and chloride ions. So it's a lot like this picture shown here. Let me slide that over, where when we initially put the salt in the water, the reaction's only going in one direction. It's dissolving and forming ions. But as this proceeds toward equilibrium, the ions accumulate in the aqueous phase such that it's energetically favorable for them to come back together into the solid. And so you have an equilibrium condition. You have some ions going out into solution and some ions coming back together and forming the solid. And that pile of salt doesn't get any smaller in the process. The concentrations stay the same over time. That's the definition of equilibrium, right? So eventually an equilibrium is set up, and instead of having the arrow only going in one direction, at saturation, you end up with an equilibrium condition. You have ions in solution going backward to the solid and vice versa, okay? So the amount of excess solid, remember, doesn't affect the position of equilibrium. And position means concentration of those individual reactants or products, okay? And remember, we ignore solids when we write an equilibrium constant. And a dissolution expression is always going to have a solid. You know, a solid dissolves to become an aqueous phase. So we ignore that. Remember, if it's products over reactants, okay, and this, by the way, is the name of our new kind of equilibrium constant. It's called Ksp. And the SP stands for solubility product constant, okay? Sometimes it's shortened just to say the solubility product, and it's specific to this situation, solids dissolving in a solvent. And for us, the solvent's water every time, okay? So let's take another example, for example. Let's take calcium fluoride, and you can see I've got a pile of calcium fluoride in this test tube with some water, and it is in the equilibrium condition. You've got some things dissolving into ions, other things returning back to form the solid. So when I would normally write the any kind of K expression, right, it's products over reactants with coefficients as exponents. But this time, our reactant is a solid. Right? We're going to ignore that and call that a 1. Oop, hold on a second. There we go. And call that a 1. Okay? Because that concentration doesn't change over time and has no effect if it's at equilibrium. If it's at saturation, has no effect on those concentrations of ions. So really, the Ksp expression looks like this. The Ksp expression is called the solubility product constant for a reason, because it's a product of the products. Notice there's the products, the ions in the top, products over reactants, coefficients as exponents, but we ignore that, that reactant at the bottom. Okay, let me check and see if there's anything else. Oh, I just wanted to show you the value for this. The Ksp is 3.4 times 10 to the negative 11, pretty small number. And so that means there's a small amount of products that actually dissolve. So if it's a small number, it tells me this stuff's not very soluble. And in fact, we can look at a table of solubility products, Ksps. So notice there it is. This is the Ksp value up here. And most of these numbers are really small. And none of these include the SNAP compounds, sodium, nitrate, ammonium, potassium, which are highly soluble because they would be all products And so the number would be huge, would just be in the thousands or even in the millions if it was highly soluble. So let's look at a couple of examples. Even things that are relatively soluble, like calcium sulfate down here, I'm looking at, has a low number. It 2.4 times 10 to the negative fifth. There are things that are vanishingly small here. Look at iron 3 hydroxide, 2.5 times 10 to the negative 39. That's so small that it's practically negligible, which tells me that iron 3 hydroxide just doesn't dissolve in water at all. It's practically insoluble. Okay, look at this one, silver sulfide, 10 to the negative 50th. That's ridiculously small. So that thing is not soluble at all. So let's take a practice here. Why don't you guys pause the video and write the Ksp expression for the dissolution of barium hydroxide solid. Okay, we're back. And if I were going to write that Ksp expression, okay, that's supposed to be a K, by the way. Ksp is going to be the product of the products, all right? And we ignore the reactants, all right? So it's going to look like this. That's an OH minus squared. So that should be what you wrote down for the Ksp expression for that. So you're going to have to be able to do some math in calculating the Ksp given the solubility of a compound. So what's shown here is an example. Let's work our way through a couple. This is calcium carbonate. You can see the solubility is pretty low, 6.2 times 10 to the negative fifth moles per liter. That's pretty insoluble. Calculate the Ksp. So that value is going to be different than the solubility. So we have to do some work. First of all, you should always write out the dissolution expression, calcium carbonate to calcium ions and carbonate. And we know some of these numbers. For example, we know the solubility of this molecule is 6.2 times 10 times 10 to the negative fifth, okay? And notice it dissolves in a 1-to-1 ratio. So we know that the number for both of these ions is going to be the same, also 6.2 times 10 to the negative fifth moles per liter. For both of those, 6.2, sorry, that's a 6 times 10 to the negative fifth. And then since we know the value of moles per liter of these ions in solution at equilibrium, we can write the Ksp expression shown here. And remember, that's just the products of the products, okay? And we have no coefficients to use as exponents here. So now we can just take these values and chunk them in there. So in other words, this expression can be written as 6.2 times 10 to the negative fifth squared, right? It's 6.2 times 10 to the negative fifth times the same number. So the value for the Ksp for calcium carbonate is 3.8 times 10 to the negative ninth. Let's see if that jibes with what we're given on our table. Calcium carbonate, 3.8 times 10 to the negative ninth, right? Spot on, pretty good. Let's look at another example, okay? Let me scroll down. So how about this? The solubility of nickel 2 hydroxide is 0.14 grams per liter. Be careful. Calculate the Ksp. So you know what to do first, right? You've got to convert mass to moles, grams to liter to moles per liter. So this is the molar mass of nickel 2 hydroxide. There's the number, that's the molarity in moles per liter at saturation for nickel 2 hydroxide, okay? And then we write the dissolution expression, and notice we're going to still write the Ksp the same, product of the products, but we do have an exponent to worry about here. Okay, and we can start to write in some numbers that we do know. Okay, we know nickel 2 hydroxide, let me draw this in blue, nickel 2 hydroxide dissolves at this concentration. So we know this number, 0.00151. Right? This number is the same, dissolves in a 1-to-1 mole ratio. So this is 0.00151 as well. But notice the hydroxide, you have 2 for every 1 molecule. So you're going to have twice that number right there. So the number for hydroxide is what? 0.00302, right? 00302. And now, once again, you write the Ksp expression looks like that, coefficients as exponents. And then we just start substituting those numbers in there. So the nickel hydroxide will be 0.00151. And then this number, which was doubled because there's twice as many hydroxide, goes in here. But notice you have to square that as well. Okay, that's a little tricky. So when I calculate that out, remember PEMDAS, right? The order of operations, exponents is second, and there's no parentheses here to worry about. So you better square this number first. To get the correct answer, the Ksp for nickel 2 hydroxide is 0.00302 squared times 0.151, and you'll get 1.4 times 10 to the negative 8th, and that should be the correct answer. Let's look at one more just in case. Once again, this is an example of one that's going to be a little tricky because it does have a coefficient here, right? So the Ksp expression is going to look like this, and you got to be careful of your numbers. So the molecule is 4 times 10 to the negative 7th moles per liter. That means this one is going to be 4 times 10 to the negative 7. But this one is going to be twice that. That's a 7, by the way. This one's going to be twice that. So that's going to be 8 times 10 to the negative 7. Okay? Then, again, chuck those numbers in there and in there. But you better square this one first because you have to square it. So it's 8 times 10 to the negative 7 squared times 4 times 10 to the negative 7. Oh, shown there. Okay, and when you crunch those numbers out, you get a really small number here. So this tells me that copper 2 hydroxide is highly insoluble. And if we go back and sort of check our data page for that, where is it? I think I went too far. There it is. Copper 2 hydroxide. What do we have? 2.6 times 10 to the negative 19. Copper 2 hydroxide right there, 2.6 times 10 to the negative 19. Hey, that's pretty good. So be careful of those and check your textbook for additional example problems and this sort of thing. Good luck.